Welcome to my presentation on unsupervised representation learning. My name is Lukas Pfahler, I'm a PhD student here at Dortmund and my research focuses mostly on unsupervised learning. Large amounts of labeled data have fueled the deep learning boom that we're currently in. You all probably know the ImageNet dataset with millions of labeled images or smaller variants like the Cypher dataset you see on the right. And at its core, deep learning is about learning the right representation for your task. So instead of manual feature engineering, you say the model has to learn a suitable representation on its own. But what do you do when you don't have label information? And that's the focus of this talk, learning representation from large amounts of unlabeled training data. In this lecture, I'll give you a non-exhaustive overview of the landscape of unsupervised representation learning. I will provide you with pointers and references and hopefully some research ideas for your own studies. And I will show you some applications and ideas from various domains. Throughout this talk, we will focus on learning tasks rather than the models. And for the most part, you can assume that the models that we need for these tasks are just very large, deep neural networks. We will focus on three different ideas for unsupervised representation learning. The first one is learning based on reconstruction. The second one will be learning based on self-supervision. And the third one is contrastive learning. And in the end, we will see an example application, and that's retrieval of mathematical expressions. So I'm happy to answer any questions in our Q&A session later. All right, before we begin, we should define some notations that I'm going to use throughout this talk. Whenever you see a small x, that's going to be a single training example. And if it's a capital X, that's going to denote the whole data set. We will use the phi symbol to denote the features, and phi is always going to be the representation that we're interested in and that we want to learn. And then if it's phi of capital X, that's just going to be the learned representation of the whole data set. Whenever you see an L, that's going to be a loss function. Usually it's clear from context what loss function I mean. And in the rare cases where we actually need to talk about the model a bit, we will have phi theta for a representation that's computed by a model that's parameterized by theta. Then some disclaimers. I will present lots of empirical results that are not based on my own experiments. So I cannot vouch for those numbers, and the results might be exaggerated, or competing results might be misrepresented, or the results may not be reproducible. I haven't checked. We're just gonna have to believe the original authors here. And also, this is in no way intended to be a complete and full summary of the field. This is just some examples from the field of unsupervised representation learning. Whenever we learn a representation, we have to ask ourselves, how do we measure the utility of this representation? I think there are like three different ways to measure the utility. First, we can use an internal measure that just looks at the representation. For instance, we might ask, how well does it compress the data set if we represent our data in a way or another? And the second one we're going to focus on in the first part of this talk is how well does the representation reconstruct the original representation. More useful probably are external measures, where we evaluate the utility of our representation based on the performance of a downstream task. For instance, we might ask, how well can we classify the data using this representation? And usually what we do then is we train a simple model like a linear model or a nearest neighbor model, and then we judge the quality of representation based on the accuracy of the classification task. Different downstream tasks might be zero-shot learning or few-shot learning, clustering, or as in our example in the end, information retrieval. And last I want to mention the visual inspection, where we judge the quality of our representation based on some 2D or 3D graphics that we might compute with t-SNE, UMAP or PCA. So those are three different algorithms for taking a higher dimensional representation and plotting them in 2 dimensions. And if it's a good representation, we're going to see some clusters that have some meaning, or maybe group all the digits that show the same digit in the MNIST dataset in the same corner of our plot. And usually that's somehow useful to look at these plots. All right. Let us begin with representation learning tasks for reconstruction. This is a technique that's really old and probably starts with PCA or singular value decomposition. Most of you will know this. For completeness, I will tell you anyhow. So maybe your original data has dependencies in it or redundancies. So look at this plot. It has 2 dimensions, but just by looking at it, you see that probably you only need one of those because one explains the other almost perfectly. So we assume that the data has a latent lower dimensional linear basis. And what we can do then is try to find a better suited coordinate system to represent this data. We can express this as an optimization problem where we have to choose 2 orthogonal matrices and a diagonal matrix that in combination expresses the data almost perfectly. And actually, there is a perfect solution to this, and so the minimum will always be 0 for all matrices. And then, as a better representation for our data, we can use the left matrix U times the diagonal matrix. What's really nice about this way to represent data is that we can actually quantify what error we make when we just use less dimensions. So we can do a rank K approximation by only using the K largest singular vectors, as we see here. And then we can quantify the error that we make, and that's just the sum of all these singular values that we didn't use. So this is really nice because it gives us a way to measure the quality of our representation efficiently. However, this works only with linear dependencies. So what can we do if we want to also capture nonlinear dependencies? One way would be to use a kernel approach here and use an algorithm like kernel PCA. I want to show you a different idea. And that brings us to the second example of auto-encoders. In auto-encoders, we say that we want a lower dimensional representation phi of x that is able to reconstruct the original data. So we train a model that's composed of 2 parts, an encoder phi that takes the data and maps it to a latent space, and a decoder that maps it back to the original space. And what we want then is that the output of the decoder is almost the same as the input. And this almost the same we quantify with a loss function. So what we do is we train encoder and decoder simultaneously over all data points in our data set, and we say that the loss between the original input and the reconstructed input should be as small as possible. And for many cases, input and output will be real valued vectors, and then the most common loss function we see is just the Euclidean distance between the original input and the computed representation, reconstruction. All right, so is this useful? Yes, we have an application for this where this actually makes a lot of sense. We are working together with physicists in gamma ray astronomy, and what we do there is we point a telescope at the sky and record events all night, and in the morning the analyst has to make sense of all the recordings. That's a lot of data, so we want to help the analyst by providing a summary of what has happened at night. And in order to do that, we use an auto-encoder to derive features of all the camera images that have been recorded at night. So we take the high-dimensional camera input that you see on the bottom and we reduce it to 256 dimensional vectors. And then using some clustering algorithm on these features, we can come up with a small summary of the night. And actually this is quite helpful because it can help the analyst to distinguish between different event classes. One of these classes is the one we're interested in, the gamma rays. And this is work that's currently under review of Sebastian Buschjäger, Philipp Honnes and Katharina Morik. We should still discuss how useful are autoencoders, because it turns out that the representations that we learn with autoencoders are not necessarily helpful for classification. And the problem is that the reconstruction error isn't the best function to measure the utility for the classification task. As you see in this plot by Alberti et al., the models that have the lowest reconstruction error don't score highest on accuracy. So the yellow and pink runs have a higher accuracy, although they have a lower reconstruction error, a higher reconstruction error. And secondly, what you see in the experiments, if you use the representation of the autoencoder and also fine-tune it to the classification task, that is, you retrain the model initialized with the autoencoder representations, then you see that the representations diverge quite dramatically from the initialization, which suggests that the representation wasn't very useful because we needed to change it a lot in order to get a higher accuracy. And one problem might be that we must encode every aspect of the data in our features in order to reconstruct every feature. And maybe most of those features aren't useful for classification, but we focus a lot of energy in reconstructing those features. So maybe we need to come up with different learning ideas. Now to something quite different that still focuses on reconstruction. So that's the similarity here. Now our data is text. And as you might know, and if you don't know, you will learn this from Sven in another lecture. When you represent text for machine learning, usually you cut it into words or tokens. So the sentence, "The fox jumps over the tree," that will guide us through this lecture, is partitioned into its words. And we want to learn a vectorial representation of this sentence. And what we do is we learn a vectorial representation that allows us to reconstruct the words with higher probability. So we say the probability that a word occurs in a sentence is given by this softmax distribution. So we take the dot product between the document representation phi of x and a representation of each word. That's w, small w. And we normalize this over all words. And then we want to maximize the probabilities of the words that actually occur in the sentence. So we optimize the negative log likelihood of generating the tokens in our data set. And we simultaneously train the document embeddings and the word embeddings. And this is based on a paper by Kwok Lee and Tomasz Mikolov. So what can we do with these document embeddings? We have shown that they are quite useful for discovering topics in a large data set of texts. In a joint study with scholars of religion, we have analyzed online discussion boards and checked what are the prevalent topics that the people in these discussion boards talk about. And for instance, we looked at this one Christian forum where they talk a lot about cooking and talk a lot about partnerships and love and marriage, but also talk about the Bible, of course. And as you should always do, sometimes this approach also fails, and we also show how we can see that in our analysis results, where we just get topics that are just gibberish and we can't make sense of them. All right. So we have seen that the representation of document embeddings allows us to group similar items in the data set. And that wasn't possible before we computed a more useful representation of the data. In principle, you can use other generative models for learning representations as well. In this summer school, you will also learn about variational auto-encoders and generative adversarial networks, and you might even learn about normalized flows. And many of these generative models can be used for extracting features. And what you would do is you just take some part of the model as your feature extractor. For instance, in the variational autoencoder, you can just use the encoder. In generative adversarial networks, you might use parts of the discriminator. And in normalized flows, you can essentially choose where you cut it up at any point. I will not go into more details, but when you listen to the other lectures on these generative models, you can have that in mind. So now I want to get into the second really nice and newer idea for unsupervised representation learning, and that's self-supervised learning. And what's impressive about self-supervised learning is that it starts to close the gap between the performance of supervised and unsupervised models for tasks like, for instance, ImageNet classification. Self-supervised learning focuses on tasks rather than models again, while the autoencoder is also a model architecture where you have this information bottleneck in the middle. Self-supervised learning is really more about generating data, training data, and measuring the success of the tasks. And designing these tasks involves creativity and domain knowledge, and not a lot of math, so it's very accessible, I think. And we are interested in learning these representations that somehow capture the semantics of our data, with the intention that in a downstream task we can use our representation to learn from a small amount of data. All right, let's look into some ideas. This is a fun task for learning a representation for images, and it's very simple. You just take an unannotated image and randomly rotate it, and then you ask the model, was this turned left, right, flipped on its head, or is it the true right orientation of the image? And as a human you can do that easily. You see the bird in the left picture and you say, oh no, gravity doesn't work like that. This image must be flipped. Or the dog is facing a weird way. This image must be flipped. But in order to do that, you seem to first detect what's in the image. Then you have some idea of how it's supposed to be oriented, and then you can predict the true label of the data. And that's the core idea of this task. In order to succeed at this task, you have to learn about object detection. And at least that's the hope. And you see what I meant by, okay, you don't need a lot of math, you just need creativity and domain knowledge, because you can come up with these tasks without a lot of math. Let's see a different task. This is coloring images. You present the model with a black and white image and you ask it to reconstruct the color. And again, in order to succeed at this task, for instance in the middle, you have to detect what kind of bug this is and how it's usually colored, or what's the usual color of this dog in the bottom row. And this one might remind you of auto-encoders, because you are asked to reconstruct an image of the same size as the input, but the difference is, while the auto-encoder would ask you to reconstruct the exact image, this one asks you to reconstruct just the color. And we can see that this is actually helping in the downstream task of ImageNet classification. What we do is we take the representation that we have learned using these two approaches, and then we learn a simple linear classifier on top of the representation. And depending on the size of the model we use, so these are 5 different AlexNet variants, we actually get quite the high top 1 accuracy. So in the first row you see the fully supervised approach that uses all the labeled information, and that gets us up to 50. But using this rotation approach already gets us to 38% accuracy, which is a really impressive result if you compare it to the other unsupervised pre-learning approaches. And you also see colorization here, which is not as good as a rotation, but it's still better than most of the other approaches. All right, so that was the first idea, and now we look into something that has become really popular, and that's tasks based on masking. It was proposed first in natural language processing in this paper, BERT, Pre-training of Deep Bidirectional Transformers for Language Understanding, and I'm sure Sven will talk a lot about this in his talk. So here's just the brief idea. You take an input and then you compute a representation, and in this case the representation has a feature vector for each token in the input sequence. So you don't have just one feature vector, but you have one for every word. And then you randomly mask some of the input tokens, so the model only sees the remaining inputs. And then you ask it to reconstruct those inputs that you have masked. So you need to predict which word was there originally. And so what does the model have to do to succeed in this task? So obviously it needs to know about words and about word probabilities, but how you would do this is you look at the context and you know that the words have dependencies and you exploit these dependencies to come up with a suitable candidate. And what's nice about this task is that you can train it on millions of text documents because those are readily available online. A slightly different variant of this task that might be a bit more efficient because you don't need to compute the distribution over a large vocabulary of words is that you just replace some of the tokens not with the masked token but with a random other token. And then you ask the model to detect at which positions did you introduce random words into the sentence. In the most basic variant, you just replace the word with a fully random word. If you want to make it more difficult, you can use a smaller language model to suggest words that seem plausible at this point and then replace not with the fully random word but with a plausible alternative and still ask the model to detect this change. And these BERT models have been really successful in the natural language processing community. You see them everywhere nowadays. And they have been successful on a wide range of tasks. That's starting at text classification, but also sequence tagging or even tasks like translation. And you can use this masking idea not only for text, but you can also use it for images. So look at this kitten, and we have masked some parts based on a grid that we put over the image. And the first idea might be we want to reconstruct the masked parts exactly like we would do in an autoencoder. So we asked for the exact pixel values of the missing pixels. Turns out that it's actually better to propose a task that's something like this. For each masked grid cell, you ask the model to choose the true patch amongst a set of distractor patches. So there are 3 patches missing, you see them on the right, and then the model has to classify for the green box which of the 3 patches is the true patch. And actually, recently there's been some theory on why this might work. Let the X white box denote the random variable where the unmasked input parts are stored, and the X black box, that's the masked parts. And those 2 variables are not independent. If they were independent, you couldn't reconstruct the masked parts, and your model actually exploits these dependencies. And now if the class label can actually explain most of this dependency, then the downstream classification task benefits from masked pre-training. So that's just the high-level idea of this paper. Predicting what you already know helps, provable self-supervised learning. And more formally, the authors show that if X white box and X black box are conditionally independent given the label Y, then the downstream task, that's the classification task that we're really interested in, has a low sample complexity. And that means you don't need a lot of training data to succeed in this downstream task. And ultimately that means that your pre-training based on masking was successful. Alright, now a short creative break. And I'm sure you have thought of your own self-supervised learning task by now, maybe for your own application that you're interested in. And I would just ask you to briefly describe it and do that in our online system. So let's look into the last approach for unsupervised learning that I want to cover, and that's contrastive learning. Contrastive learning can be summarized in a figure like this. You take one input example X and then you extract two different views of the same object X randomly. And then you compute a representation of each of these views, and you want to maximize the similarity between the two representations, and you use a loss function to quantify this similarity. Usually what we do to get views is use some sort of data augmentation techniques. For instance, you might take the same image and distort the colors in two different ways. But we'll see other ideas shortly. And we might also use two different sorts of views. So I've mentioned two views based on images, but you might also take a video X and extract the audio X1 and the images X2. And of course, then you need two different models to compute the representations. And we denote this here by phi and phi prime, as well as v and v prime. All right. In all these approaches, you need negative samples. So what we do is we contrast the similarity of X1 and X2. And if we don't use negative samples, you can achieve perfect similarity if you map each input just to a constant vector. Then everything looks the same all the time, and judged by your loss, you have a perfect model that can capture all the similarities you've shown it. Obviously, this model is absolutely useless, so what we need to do is also use negative examples where we want a small similarity. And we denote these by a x minus. And for technical reasons, we require that all the norms of our feature representations are controlled, and what you usually do is you map all the inputs onto the hypersphere by just normalizing all the feature representations by their two norm. And we will see why this makes a lot of sense when we look at the first loss function that's popular in these contrastive learning schemes. And that's the triplet margin loss. And what we want here is that the similarities between the two views should be higher by a constant margin of 1 compared to the similarity of x1 and the negative example x minus. And that's exactly what you express in this loss function. It looks a lot like a hinge loss function that you might know from support vector machines. That is just because the loss is 0 when you fulfill this margin of 1, and it's the difference of 1 and the margin you actually have in case you don't fulfill the margin. And here you see why it's important that the norms are actually controlled, because if you don't control the norm, you can just fulfill arbitrary margins by just scaling all your outputs as soon as you have fulfilled the margin. So obviously that's also not useful and will just lead to very large norms in your random features. And probably the most popular loss function is not the triplet margin loss, but the info NCE loss. That's info noise contrastive estimation. And what we do here is we identify the view of the same object, so that's the view of x2, among all other views that we have in the mini batch. So that's essentially not just one negative example, x minus, but we use a large batch of views, and usually the larger the batch, the better this works. In literature you can find batch sizes that go up to over 4,000, and they still outperform the larger ones. Alright, looking at this loss function, you probably see that it looks familiar. This is because it's essentially the cross entropy loss, where the classes are given by all the examples in your mini batch, and the model task is to select the true class, and the true class is corresponds to the second view in your data. So you have again reduced your representation learning task to a classification task. And an example of this is word2vec. Word2vec is much older than the terminology contrastive learning. I still want to present it here. And what we do is we train representations of words. This is again in natural language processing, and there you have this problem that usually you can't judge the similarity between two words. All you could do prior to word embeddings was check if it's exactly the same word or if it's a different word. And with word embeddings, you kind of get a continuous scale of similarity between words. And what we do is we take the sentence X, we sample two views, X and X2, that appear in the same context. And the context in this scenario is just a range of words. You might say that words that appear within two tokens are in the same context. And then we sample a negative example that's further away from the positive example. And then we ask the model to classify that jumps is close to fox, so that's output class 1, and that tree is far away, so the model is supposed to output -1. So you see, this is essentially all that I've just presented you in the slide before. So now to something cooler. We look at image augmentation for creating views. These are all the augmentations that you also use in supervised learning, and they are built into your deep learning frameworks like TensorFlow or PyTorch, and usually you use them during training to generate small perturbations of your inputs to make your model more robust. But we use them to extract different views, and what you might do is crop parts out of an image, resize it, distort the colors a bit, do some rotations, mask some parts, blur a bit. So all these standard image augmentations. And then what you do is you take two different random augmentations, and then you ask the model to learn a representation that puts both views in a similar area of your representation space. So in this example, we have the dog, and we use two different augmentations that we've randomly sampled. We compute a representation with the same model, and then we train the model such that the views are put into the same direction. And the results of this were really impressive. Compared with the supervised model that's in the top left, that scores a little above 75% accuracy on ImageNet classification. If we use a linear classifier based on the representations that we have learned this way, we can score almost an accuracy of 70%. But if we increase our model size, so these are all ResNets 50, and they have this scaling parameter where you can blow up the number of parameters that the model actually uses. So if we do this during pre-training, we can approach the accuracy of the supervised model. So if we use 16 times the parameter count, we are essentially on par with the supervised model. However, we use the training labels only in the second downstream task. All the convolutions are trained just on unsupervised data. And this is really impressive and gets us back to the entry statement that I made to the self-supervised learning, that it's really closing the gap between supervised and unsupervised methods. You also see the rotation approach that I've presented earlier in this plot. It uses the AlexNet architecture that's roughly 100 million parameters, and you see quite a substantial improvement using the contrastive learning in comparison to the rotation approach. Another example for these views are views extracted from video. The paper I show you here, what they want to do is they want to train a robot to pour a glass of liquid into another glass based on camera inputs. So in the first step, they want to learn a representation of the video stream or of the keyframes in the video. And here we extract similar views by extracting frames that are within a time frame of another, and we sample the negative examples by selecting frames that are further away time-wise. Obviously, it's really simple to generate training data this way. You can just use the video and extract frames. So what does this remind you of? This idea of a small context that's positive and everything that's further away that's negative. Leave your replies in our online system. So I've shown you quite a few ideas of creating views that you can use for contrastive learning. So I'm sure you have thought of your own ways to extract views for contrastive learning tasks in your own applications. Maybe you can write them up in our online system as well. Let us briefly discuss some of the theory that's behind contrastive learning. First of all, a popular way to explain the success of these methods is saying that the loss function that we're optimizing is the lower bound on mutual information. Or put differently, what we optimize is a high mutual information between the differing views. Unfortunately, that's not all there is to it, because we can actually see that if we optimize a tighter bound on the mutual information, we get worse downstream performance. So apparently optimizing mutual information is not all that's important. I want to close this section with a different approach to contrastive learning. That's called Bootstrap Your Own Latents. How it works is essentially in the title. So this is a bootstrapping approach. What's bootstrapping? Normally that's a interactive procedure where we use the predictions of an older model as the ground truth label for training a new model. So we're not worried about supervised classification, but we still use old representations, and what we want is that our current model, the representation that the current model computes is similar to the representation of the old model of a different view of the same object. We don't actually train this system in epochs, but instead of using a fixed older model, we simulate this aging of the model by using a running mean of the parameters of the model. So that means that this theta bar is always lagging behind theta a bit, and this is thus the old model. And what is really nice about this approach is that you don't actually need negative examples. You just fit your new model to the information of the old model. And according to the authors, this works ridiculously well. They use the same augmentations that I've shown you before. That's the SimCLR paper in this plot. But the Bootstrap, your own Latents approach, works still quite a lot better. And you see that when you increase the number of parameters, the gap between the supervised model and the self-supervised model shrinks even further. And you can get above 78% accuracy on ImageNet classification with this unsupervised approach, which is really impressive. And again, these are ResNet 50s for anyone who's interested. All right, I want to close with a recap question. We have seen quite some approaches in this presentation, and I would ask you to label the edges in this small graph and label the edges with similarities or common properties of the approaches. All right. The last section is where I want to present our approach for mathematical retrieval that is based on unsupervised representation learning. So the goal is to develop a search engine for mathematical expressions. And any search engine that has success in this area has to generalize between different notations and conventions, and be able to match parts of formulas that don't, while ignoring other parts that are a mismatch. And the system has to apply background knowledge on these conventions and notations. And that's why we want to use unsupervised representation learning to tackle this problem. And we use millions of formulas that we have crawled online to train our system to do the task. We work on raw data from more than 900,000 papers that are hosted on arxiv.org. That's this popular preprint service. And the nice thing about the archive is that we don't actually need to process PDFs, but we can work directly on LaTeX sources. So the formulas are actually available in a text form to us. And this way we extracted more than 29 million formulas from LaTeX. But no similarity labels are available. Hence the need for an unsupervised machine learning task. Our data flow works like this. We start with the formula on the left that's represented as LaTeX, so that's a text essentially. We don't like this textual representation because it contains a lot of user-defined macros, and there are a lot of ways to express the same formula in LaTeX. So what we do as a first pre-processing step is we compile it to MathML. That's an XML format that has only 30 different tags and encodes most of the symbols in Unicode. So that's, I think, a much nicer representation of math. XML files are a tree structure, so our model has to deal with trees, and a suitable choice for model there is the graph convolutional neural network. And there's also a lecture on graph convolutional neural networks in the summer school, so check that out if you're interested. And the graph convolutional neural network outputs a vectorial embedding of the math using some sort of pooling operation. And we actually train two different tasks at once. And the first one is a contextual similarity task, like the word embeddings or the contrastive learning from videos. There we say that two formulas are similar when they appear in the same paper, and we randomly sample negative examples uniformly and random. So we might summarize this as trying to find a mapping between MathML structures and the co-occurrence information of formulas in papers. And I want to show you one more loss function that we found works better than the hinge loss function that I've shown you earlier, and that's the histogram loss. And what we do here is we build two histograms based on a mini batch, one for all the similarities between the positive examples and one for all the similarities to the negative examples. And then we penalize these histograms such that the positive example histogram leans a bit more to the right and has higher values than the other histogram. The second task we use is this masked language modeling task inspired by the BERT model. So we use the same masking approach where we mask some of the tokens in our MathML tree and ask the model to reconstruct it. Again, you as a trained scientist can probably do this with quite a high accuracy, because you look at this and you see, oh, this is some sort of linear classification model. So usually what we do here is we use the W or the beta for the parameter vector. And also we know that the green and the blue box are probably the same character. And so we can do that using our training on math and machine learning. But the model has to come up with a strategy to do this based on a lot of data. Using this system, we have run a small search engine study where we have crowdsourced some formulas that are provided with labels. We have asked our colleagues from different disciplines to do this for us. And this allowed us to do a quick study where we see that our model outperforms a strong baseline that is just essentially treating this problem as a text search, and we outperform this baseline quite substantially, looking at precision and mean average precision. Here's a small example of why masked search might be superior to keyword search. What we do is we query for the Ising model formula, that's the top row, and we see that the top two results are a formula of the Boltzmann machine and of the Ising model. And these two models are very highly related. Looking at the math, not knowing what's described, you see that it's an almost perfect match. And these connections are known in literature, but had you not known that, you might have only queried the Ising model and not looked at Boltzmann, and so you might have a blind spot there. Querying for math gives you these results immediately. We have a demo of our system running. You can find the link at my GitHub page. I encourage you to check it out and search for math in 900,000 papers. Thank you for your time and see you in our Q&A session later.